In this work, we present a method for learning spatial preferences from tidied scenes. First, let's motivate this method. Many everyday tasks that we would like a robot to perform can be formulated as a rearrangement problem. Given a set of objects, arrange them into some goal state. Examples include tidying your room, loading a dishwasher, unpacking new groceries into your fridge, or setting a dinner table. But how does the robot know what that goal state should be? Even though most people have a similar set of objects in their rooms, everyone arranges them in their own personal way. Here's the key idea of the paper. By observing tidied scenes, our NeatNet model can infer a user preference vector and use it to generate a personalized arrangement for any set of objects. NeatNet uses this preference vector to tidy a known scene, place a new item, or arrange a new scene in a personalized way. Let's now look at how NeatNet works in more detail. The goal is to infer a user's tidying preferences represented as a single vector. Users whose vectors are close together in the latent space share similar tidying preferences. Now, this latent vector may not always be interpretable, but perhaps it can capture features such as whether the user is left or right-handed, or whether they prefer convenience over aesthetics. To learn from objects and scenes, we need to encode them as vectors. The encoding for one object consists of its semantic embedding, which captures the object's identity, and also its position encoding. The semantic embedding for each object is generated from its name. Note that objects whose names appear in similar linguistic contexts are arranged in a similar way, for example salt and pepper or pen and pencil. We use a pre-trained natural language processing model to get a wording vectoring vector for each object, and then we train our own network end-to-end to generate a semantic embedding which is useful specifically for tidying. Our method learns two functions, an encoder and a position predictor. The encoder takes the user's arrangement of the scene and infers a user preference vector. The position predictor, which acts as the decoder, outputs an arrangement of the scene based on those preferences. This network can be trained as a variational autoencoder. Here is the architecture of the encoder. The input is an example scene arranged by the user, represented as a fully connected graph. Since each scene can have a variable number of objects, we use graph attention layers to encode the scene and extract the user's preferences. The position predictor acts as the decoder. This time, the input is a graph of the objects for which we want to predict positions, combined with the user preference vector. Graph attention layers are used to predict a tidy position for each object. We developed a rearrangement simulator to gather data for evaluating our method. Its intuitive controls and deployment as a web app make it possible to gather large-scale data from human users. Each user arranges several scenes, placing each object one by one and submitting the tidy arrangement to our cloud database. Users arranged 4 scenes. 2 are abstract, where users have to line up objects. They can do so either by shape or by color. And 2 are real scenes, a dining room and an office. We will now discuss some visualizations of interesting results. We noticed that an individual example of a scene arranged by a user could be noisy. NeatNet infers the user's preferences from their example and combines this with prior knowledge from similar users. Therefore, it corrects for noise and produces tidy reconstructions of the scene. Here, NeatNet is placing a new object, the laptop. If you placed the laptop in the same way as you placed a desktop computer, you would get an inconvenient arrangement. NeatNet knows that the laptop also shares some semantic features with a keyboard and a monitor, so it places the laptop in a more convenient way. Our method can also observe how the user arranges one scene, infer their preferences, and use this to predict how they would arrange a new scene. NeatNet generates tidy and personalized arrangements, showing that it can learn some preferences which transfer across scenes. We can also see some patterns in the user latent space, such as clusters of left and right-handed users. We have seen how NeatNet can infer a user's spatial preferences and use this to predict tidy positions for any set of objects. This adds a layer of personalization to the canonical task of robotic rearrangement.